So my name is Oliver, and I work for Wolfram Research in the numerics group. So I mostly work on the finite element method, PDE modeling, NDSolve, and things like that. And today I'm going to be presenting about solid mechanics, which is a sub-project in the PDE modeling framework. And yeah, I'm going to show you what's new here. So the title in the agenda is actually structural mechanics, but I've narrowed it down a bit further to solid mechanics, so that we're only going to talk about mechanics of solids and not frames and shells and things like that. If you have been in the conference, in the previous conference, you might have seen previous talks on these topics. So in version 12, we introduced acoustics and heat transfer as PDE modeling areas. In 12.1, we've added mass transport. And at that point, we just directly used the equations like you'd type them out and plug them into NDSolve and got a solution. In 12.2, we added a basic framework for doing PDE modeling. And at that time, the acoustics, the heat transfer, and the mass transport PDE models got rewritten to use this PDE modeling framework. That sequence of steps was necessary for us to first learn a bit how PDE modeling should be done and things like that. So that's why we first did some experiments with the modeling, and then we finally built the framework. So in version 13, you're going to see new electromagnetics PDE models. There's no theory tutorial yet, but there's some electromagnetics tutorials about electromagnetics. I'm not going to talk about those today. What I'm going to be talking about is the experimental addition of solid mechanics. So when I speak about these PDE modeling things, there's typically, several things. So PDE models typically consist of a notebook that has a background theory type of content that explains the field of physics a bit and explains what can be done there and how it should be done. And then there's a model collection that shows application examples. So we've done this for acoustics, heat transfer, some parts of chemical reactions like with the mass transport, electromagnetics, and now in 13 we've added solid mechanics. So if you want to start looking into the PDE modeling capabilities of Mathematica, probably the best way to start is the PDE models overview. So what I've here is the documentation system, and if you type PDE models, you get this PDE models overview page, and there you see the various fields of physics that we've already tackled. And typically you'll find this has a guide page. So if you click on that, you'll get to the heat transfer and PDEs guide page with some additional information. Then there is a tutorial or like a monograph on heat transfer, on how that's actually modeled, the theory. In this case, we have some verification tests, and here is some application examples that you can look at. Right, so maybe at this point I can actually point out, so for the electromagnetics, there's two new application examples that you can look at. But today, what I want to talk about is the new addition down here, which is structural mechanics and the subcategory of solid mechanics. So we have a guide page again. There's a large tutorial about solid mechanics and some verification tests and models that we're going to discuss. Okay, going back to the presentation. Right, so when we speak of a field of physics and PDE modeling in that area, what we typically do is that you have a function that's called XYZ PDE components. This function gets the dependent and independent variables and some parameters, typically material parameters, and will return the core PDE for this field of physics. Then there's boundary conditions, the XYZ condition, XYZ value, and they work after the principle that you first specify the predicate where this condition is going to be active on the geometry that you'd like to model, and gets vars and pars, which are the same as for the PDE component. Now, something that ends in condition will always generate a Dirichlet condition, and something that ends in value will always generate a Neumann value. But we'll see this in a second. So to get us started, I have a very simple overview example. So we have a solid beam that's fixed on the left-hand side, and we have a force in the negative z direction. And we want to model this, and we want to see what this looks like. So the geometry is really simple in this case. It's just a cuboid, so nothing spectacular here. Now we set up the variables and the parameters. So for solid mechanics, we're generating a system of PDEs. In 3D, this is 3 dependent variables, u, v, and w, and they're the displacement in the x, y, and z direction respectively. So this is what we're looking for. And that will become apparent in a minute, what that actually means. And then the independent variables x, y, z. In this case, I've just specified as parameters material titanium, and the PD generation code will extract all material data it needs from this entity, titanium. So if you don't find the entity of the material that you want to model with, that's not a problem. You can specify all material parameters as well, like Young modulus or Poisson ratio, thermal expansion, whatnot. So all of those can be specified, but it's quite convenient to actually have this material specification that simple. The next thing we do is we call the function solid mechanics PDE component with the variables and parameters we've just specified, and that gives a PDE operator. It's just the left-hand side of the PDE, and this is what it looks for this specific case for titanium. So this is it's a large set of PDEs. And previously you'd had to type all this manually, but now you can just call the function and it will generate the proper code for you. Now for the boundary conditions, in this case, we have 2 conditions. So we have a solid boundary load value that's applied at the right-hand side, x equals 10, bars and pars as before. And now we can specify a force. And as we say that the force is 0 in the x, 0 in the y, and minus 1000 Newton in the z direction. And that will generate 3 Neumann values. So Neumann, the first one is 0, as we specified here. The second one is 0 as well, in the x and y direction. In the z direction, we get the 1000 divided by basically the surface of that part where this boundary condition is active. So because we wanted to specify a force here, it needs to be rearranged to become a pressure. So you could very well have specified pressure here, and then this renormalization to the area wouldn't happen. So either force or pressure can be specified. Solid fixed condition. So on the left-hand side, we say the vars and pars means that there is no movement in the x, y, and z direction. So the solution there for u, v, and w is 0. Next thing is we'll plug this system of equations into NDSolve. Again, the dependent variables are u, v, and w over the domain we specified. NDSolve, as usual, returns 3 interpolating functions. And the solution is, if you imagine a point px, py, pz somewhere in the domain, and if you add the u, v, and w components, that will give you the displacement of the object after the force is applied. So the visualization team added these nice vector displacement plots, and it's very simple now to specify this computed beam displacement, plug it into the vector displacement plot over the geometry, and there you have the exaggerated visualization. Now, as Tim already pointed out in his talk yesterday, these visualizations are exaggerated because typically for material deformations, the deformation is so small you wouldn't even see it. So we need some exaggeration to actually see a quantitative behavior of this form. All right, so that's the really rough workflow. What we hadn't seen in previous PDE fields of physics is that this one, the solid mechanics, has companion functions. So the solid mechanics PD component generates the displacement in principle when you plug it into NDSolve. The solid mechanics strain takes vars and pars as for the PD component and the displacement we've just computed, and will give us the strain in that object. And the second function is the solid mechanics stress. vars parse and gets the the strain from the previous computation and will return the stress. So let's have a look at what that looks like. So solid mechanics strain vars parse beam displacement will return strains, and the strains are a symmetrized array. Now, the meaning of the symmetrized array, which is a dimension 3 by 3, is the strain matrix. So on the diagonal, we have the normal strains, and on the off diagonals, we have the shear strains. Now, one thing to be careful about is that we're using engineering strains. So these are the gammas, and the relation of the engineering strains to the strain tensor is by a factor of 2. So this is just something to keep in mind. Right. So if you wanted to plot, say, the strain in the XX direction, you'd call something like slice contour plot and extract that part of the symmetrized array to visualize this. So this is the strain in the 1, 1 on the XX direction. Same thing for stress. So solid mechanics stress, vars parse, and now the strain we've just computed. Again, this returns a symmetrized array, which again, in this case is symmetric. Doesn't have to be, but in this case it is. Here we have the normal stresses on the diagonal and the shear stresses on the off diagonals. And again, if you want to visualize this, for example, so in this case, I've visualized the XY stress with a slice contour plot. So same thing. All right, so this is basically how it works. Now we're getting into a bit more complicated area. So now what we want to do is we want to couple solid mechanics and heat transfer to do some thermoelasticity. And for that, I have an example here where we have a compound. So the top part is aluminum and the lower part is titanium. That is heated on the left-hand side to 100 degrees. And because aluminum has a larger thermal expansion than titanium, this thing is going to bend. Also, to make it a bit more interesting, we have a flow on top and below to take heat away. So I've generated a mesh with 2 regions. Don't want to go into details here of mesh generation, but you can look at this. You can open the cell and see the code, or you look at the tutorials. To do the actual PDE modeling, we now have solid mechanics variables, U and V. So we have a 2D problem now, and we're going to do a plain stress problem for this case. So U and V is in 2-dimension, the displacement, and the thermal variable is T, again in X and Y as an independent variable. Okay, the parameter setup is again quite simple. So we have the material, and now we specify a list of 2 materials. The first one is a predicate where this material applies. So Y larger, some kind of value will have an aluminum, and if it's lower this value, then we have titanium. Now, the next thing is, so because we want to couple the solid mechanics to the thermal expansion, to the thermal part of the problem, the thermal strain needs to know what the thermal variable is, and that's what we specify here. It's just the variable. And if you do a pure solid mechanics problem and want to add a thermal strain, you could just enter a number here or an interpolating function or something like that. But because we want to couple it with a different field of physics, we'll just enter the variable of the dependent variable here. And we specify a thickness in this case. Okay. So just to look at this again, the thermal expansion of aluminum is larger than that of titanium, just to verify that. And again, all the material data the model needs is actually extracted from these elements. And that's probably something you can expect in a future version that we're going to extend on the material database that we have for these cases. Okay, now let's look at the actual PDE model. So again, we have a solid mechanics PDE component, solid mechanics variables, parameters, and there's no other forces involved. We hold this thing fixed on the left-hand side. Now we add the heat transfer PDE component with the temperature variables, and again, the same parameters. On the right-hand side, we have a heat transfer value. So on the lower and the upper part of this these beams, T-vars, parameters, we have a heat transfer coefficient of 5 watt per square meter Kelvin and an ambient temperature of 15 degrees. So that's where the heat is dissipating on top and at the bottom of the beam. And the last but not least, we have the heat temperature condition on the left-hand side. So we specify a surface temperature of 100 degrees. So when we compute this, we plug it into NDSolve. Takes less than a second to compute. So UV is the displacement again, and T is the temperature distribution. And we can look at this. Again, we use the vector displacement plot. So this is the deformation here. So it's bending downwards, which is expected because the aluminum is the top part. And here in the temperature plot, we see the temperature distribution in the two materials. Okay, so that's another example. Oh, right, so I forgot. So if we want to compute the strains, we'll use the displacement solution we got, UV and V, and plug it into the strains, can contour plot again, and the same thing for the stress, with a small exception that previously we had the thermal strain temperature to the symbolic value. Now we use the interpolating function we just computed. So we replace that. And here's an example of computing the von Mises stress, contour plot of the von Mises stress for this specific situation. Okay. So now we've seen two stationary examples, but that's not where it stops. So we have different analysis types. Here's an eigenmodes analysis. And to make things a bit more interesting, I've chosen to import a step file format. So this is not something that I've created, but this is something that I've imported. And I've generated the boundary element for the mesh for this. So that's what it is. And we want to do an eigenmode analysis of this. So I've generated a mesh, and I've chosen a first order mesh just so that it doesn't take too long to compute. So if you want to run this, you don't have to wait for too long. So eigenmode analysis works by specifying U, V, and W, but now you also have a time variable, T here, in the variables. The material is again titanium, and I specify that I want to do the analysis type is an eigenmode analysis. I put this in the solid mechanics PDE component. It will generate you the proper PDE for that. And we'll plug it into NDEigensystem, set this all to 0 because there's no external forces. The dependent variables, time variable, the mesh, and we want 12 eigenvalues. And when we look at those after the computation, we scale them with the square root and 2 pi to get the eigenfrequencies. And we see that the first 6 of them are 0. And that's because this is an unconstrained eigensystem. So there's no Dirichlet condition that holds this object in place. And the next 6 eigenvalues are real eigenmodes. And this is a visualization of the next 6 eigenmodes of this object. But just a different analysis type I wanted to show. So nonlinear elastic materials. So far we've seen elastic material, linear elastic materials, but I wanted to show a nonlinear elastic material. In this case, we have a block that's on roller constraints on the bottom and on the left. So it can move in this direction, and it can move up and down, but it cannot further move in this direction here. The reason I show this is twofold, and we'll get to that. So the region again is simple, it's a rectangle. The variables is UV, it's like a 2D problem. And now I've written a material model function. So vars parse and get some data. This is a hypoelastic material model. It's not a hyper, but hypoelastic material model. And you can go ahead and plug this material model that you've written yourself into this parameter section. So a material model function is this material model. I don't want to show the exact details. You can uniconize this and look at the mess of it. It's complicated, but I want to show that this works. The model form is a plane strain this time. Thickness is set to 1. And we specify a PDE. We have the solid boundary load value on the right-hand side. and a pressure P. So this P, note, is symbolic. It's not a fixed value. And the reason for that is that I want to plug this into a parametric NDSolve. So the parameter P, the pressure on the right-hand side, is now a parameter. And I can use this parametric function that parametric NDSolve generates and run this from 1 to 20. So the pressure increases from 1 to 20 in steps of 1. And I'll compute the solution at a specific point somewhere here, just to get some data. And what you see here now is the force displacement plot. So as I increase the force, or the pressure, actually I should say pressure here, as I increase the force, the displacement slowly starts to increase further. So this is a highly nonlinear problem. So that's also doable. Let me show here. Right, so a few more things I want to mention is, so the analysis types, we've seen a stationary analysis. We can also do transient analysis. We've seen an eigenmode analysis. We can do frequency response analysis, parametric analysis. I've shown an example of that. I also want to talk a bit more about the material models. So what there is going to be for 13 is that we are having linear, elastic, isotropic, orthotropic, and anisotropic models in 2D and 3D, and they can contain thermal expansions. What I'm not quite sure about yet is whether we're going to have the nonlinear elastic, the hypoelastic material model that I've shown here in the version 13 quite yet. I'll need to think a bit about that. Maybe not. I'm not quite sure yet. What we're not going to have is large deformation. So for hyperelastic materials, that's something that's going to come in the future version. One thing I'd like to mention is the solid mechanics components are in experimental status. The reason for that being that when I add the nonlinear material models, I'm not 100% sure that I can really maintain the interface like I've designed it. So there is a small chance that I need to change this. And because I don't want to interrupt people's work too much, so we decided to make this experimental. I hope that I don't have to change it, but there is a chance that I need to change something. But I'll really try not to change anything in the interface of the functions. But we'll see what the future holds. Right, one other thing I want to mention is, so we've seen a step file import, but that's not the end of it. We have Open Cascade link, and Open Cascade is a complete CAD engine. So this helical bevel gear is something that I've generated entirely within the Wolfram language. So you can generate complicated geometries in the language itself. And I'm trying to push this further so that we have even more capabilities. But this is, look at the Open Cascade link tutorial. It's quite impressive what can already be done here. Right, so let's see. Before I conclude, I'd like to shout out to Mauricio Fernandez and Craig Carter. Both of them were really great sparring partners while I was developing these functions and the functionality. Thanks a lot for that. The functionality wouldn't be what it is if I hadn't had a chance to talk with you. So that basically concludes my presentation. I thank you very much for your attention. The starting point, again, is the Packlet Guide PDE Modeling, or the PDE Models Tutorials PDE Models Overview. If you have questions, or if you are into PDE modeling, if you do solid mechanics, please contact me. My email is not a secret. I enjoy working with people. So even if you just want to say hi, and even if you don't like the functionality, that's also of interest for me, of course. Just don't be shy, contact me. So that concludes my talk. And I think I'd like Andy to help me with the questions now,
sure,
if there are any.
There's a couple questions. Shane asks, are surface forces just as easy?
So surface forces. I need to try to put this in context. So let me see where.
He clarifies relative to point forces.
Right. So the forces that we actually do they are surface forces. So the Neumann value that I've generated is a surface force. If you wanted to do point forces, you'd have to do this with a Dirichlet condition by specifying a fixed displacement. And there is a function to do that. That's called solid mechanics displacement condition, where you can specify that a certain point should have a certain displacement. But the solid mechanics load value is a surface force. I hope that clarifies it.
Paratosh asks, and this is a two-sided question, given that you are specifying force in newtons, do we assume that the units for X, Y, Z are in meters? Is there a need to specify units for the independent variables?
Okay, so units, yes, good question. Glad you asked this. So yes, internally, all PDE model functions convert to SI units, SI base units. So that has a consequence. So if you specify, even if you don't specify material parameters in quantities, you need to be aware that if you have a mesh that's not specified in the units of meters, things are not going to match up. So the geometry needs to have the same units as the PDE model. There is functionality to change that. So there is an option, I think it's called scaling units, and I'd refer you to the reference page or the tutorial that explains how that's done. So if you have a geometry that you imported from somewhere and it's in millimeters, which is not uncommon, you'd have to rescale the PDE, but there is an option to do that, and then it will automatically convert this to millimeters as a length unit. Again, that's also probably something I'd like to work on for a future version, where I'd like to have element mesh be more aware of units, so that if you import a step file format that has units, and typically they do have units, that you immediately know that this mesh or this geometry is in what units, whatever, so that you're aware of it. Okay.
Probably have time for one more question.
Mm-hmm.
Thomas asks, how easy would it be for .obj, I just lost the question, .obj or .dxf import be to work with?
Should be easy. You'd use the import functionality that's already in Mathematica, and that will be able to import it into a mesh region or a boundary mesh region or some such, and then you can go from there.
Thomas also asks, could you work with a model pulled out of System Modeler?
So System Modeler does something a bit different. So it doesn't do solid mechanics in the sense that I've done it. So there you have a collection of objects that interact. It's more on an ODE level, while we're doing more PDE level. So I'm not aware that System Modeler can have solid objects in it, but I might be wrong here. I'd need to check this with the System Modeler people to give a definite answer on this one.
You may want to could you refer to your links once again for anyone that has further questions?
Oh, I'm sorry. Yeah. So what you could do is you later this afternoon we have a numerics office hour. You could come and visit there, or send me an email and we make a private meeting or something like that. That's the options you have. Yeah.
Beautiful. Okay. Thank you very much, Oliver.
Thank you. Have a good day.